All right, so in this module, we're going to be talking about semantics. So we've started talking about syntax in propositional logic, and we defined formulas, propositional formulas, which basically take propositional symbols and logical connectives and put them together and symbolically create something that we call a formula. And then that was kind of a syntactic view of things where we didn't assign any meanings. There was no meanings for anything. It was just symbols. And what we would like to do in this module is we're trying to assign meanings to those syntactical formulas that we defined. And that corresponds to semantics. So in this module, we're going to be talking about semantics and giving meanings to those formulas. And in general, in this lecture, we're going to have a good number of definitions. So I'm going to write out those definitions in a separate whiteboard so we can keep track of them. But a good number of definitions are coming up, especially in this module. And let's start with some of them. So the first definition is a definition of a model. And this is a very poor choice of word. We've been using the word model throughout the lectures of this class as a different thing, right? Like we talked about modeling, inference, and learning. But in the logic lecture, we're going to assign a different meaning to the word model. And that has historical reasons, because historically, like model has been used in these settings in logic in this particular way to refer to assignments, really. So a model for this lecture and for the logic lecture, let's refer to a model in propositional logic as an assignment of truth values to propositional symbols. So I'm going to use the word W for a model, W for world. So that's why it's called W. So a model W in propositional logic is just an assignment of truth values. Okay, so what does that mean? So let's look at an example. For example, let's say we have 3 propositional symbols, A, B, and C. Okay, how many models do we have? Well, we can have 8 possible models, right? 2 to the 3 possible models or worlds that we can live in. And a particular W, a particular model, is going to be a particular assignment. So for example, I can pick A equal to 0, B equal to 1, and C equal to 0, and that's a model. That is one W that corresponds to an assignment of truth values to propositional symbols. Okay, so let me write that on our whiteboard here. So going back here, I'm going to start under semantics, and then we have the word model. Model, and I'm going to use the word W for it. Okay. All right. Let's go back. All right, so now we are ready to define this thing that's called interpretation function. And an interpretation function is the thing that actually gives us semantics and gives us meaning. So what is an interpretation function? So let F be a formula. That's what we defined in syntax. And let W be a model, okay? So an assignment. So an interpretation function, I, gets a formula, gets a model, and it basically outputs true or false. It basically tells us if W satisfies F or if W doesn't satisfy F. Okay, so interpretation function is really the thing that binds formulas and models. Formulas living in the syntactic land and models living in the semantic land. And basically interpretation function is trying to like connect them and tell us if that is true or not. So let me go back here and let me write out interpretation function. Interpretation function. So it's a function I that takes F, a formula, and W, and it gives us true or false. So let me go here and show this. So let's say that we have a formula F. I'm going to write or draw our formulas using these rectangles. So in the syntactic land, we might have a number of formulas. Let's say I have one formula F. And in the world of semantics, we might have different models, right? These are different models or worlds that we can live in, or worlds. And I can pick a specific one. Let me call that W. No. Okay, let me call that W. And what I can do is I can basically connect a formula to this W using this interpretation function. So I'm going to have an interpretation function F and W that gives me true or false if F satisfies W or not. Okay, I can have other W's in this space of models, in this semantic land. So how do we define an interpretation function? So the way we define an interpretation function is recursively in a similar way that we defined our syntax. So we're going to start with propositional symbols. So we have these propositional symbols A, B, and C, right? Like these take Boolean values. And the interpretation function of each one of these propositional symbols P, and a model W is just going to return W of that propositional symbol. Okay, remember W is an assignment to these. So going back here, let me give you an example. So my W is going to be an assignment that maybe says A takes the value 0. Okay, and my propositional symbol is just A, right? So if I look at interpretation function over P and W, it's basically checking interpreting A and the model A being assigned to equal to 0, and that returns the value 0. Okay, so that is just for the base case of this. Okay, so then when we think about more general formulas, these formulas, how are they defined? They're defined based on these logical connectives applied over propositional symbols, and based on that, we can basically recursively define this interpretation function. So I can have a formula F and a formula G, and I can create kind of this truth table. And interpretation function of F and W could take value 0 or 1. Interpretation function of G and W could take value 0 or 1. And then for anything else, like for any of these other logical connectives, I can basically recursively define them. So what would be an interpretation function of negation of F and W? It would basically try to negate this column, right? So it would be 1, 1, 0, 0. Or if I'm thinking about interpretation of F and G, well, what would that be? And the model W, what would that be? That would be interpretation function of F and W and interpretation of G and W. So basically adding these two columns, and that gives us these values. And so on. Similarly, we can define interpretation function over F or G, or F implying G, or F bidirectional implication of G, and so on. And then we can kind of assign meanings to these more generic formulas. Okay. All right. So let's look at an example of how do we do this recursively. So let's say we have a formula F, and that formula is negation of A and B and bidirectional implication C. Okay. So that's my formula. I have an assignment, I have a model. That model is truth assignment to my propositional symbols A, B, and C. So let's say A is 1, B is 1, and C is equal to 0. And now I can call an interpretation function F and W and see what the value of that would be. How do we do that? Well, let's start with these nodes. So at this node, I can call interpretation function over symbol A and W. Well, what is that equal to? Well, that is equal to just 1, because I'm just going to call my table of models, right? I already have this. That's just equal to 1. The negation of A is going to be equal to 0. What is interpretation function of B and W? Well, again, I have an assignment. I have a model. That tells me B takes value 1, so that's 1. And then if I'm taking an interpretation function of negation of A and B, then that is an the AND of these two. So 1 and 0 gives me 0. Similarly, I can look at interpretation function of C and W, reading that off my model, that is equal to 0. And then when I'm looking at equivalence of this C and negation of A and B, well, these two are equivalent, so that's just going to be equal to 1. Okay, so this is just showing recursively how do we run interpretation function. See, there's no learning here. This is like defined by logic, right? Like you can define your own logic, that would be fun. But this is defined by some sort of logic that is this propositional logic that we have defined using our formulas and using our connectives and so on. And I'm just like calling this, like I'm just computing this. So I'm not doing anything like fancy here. All right, so each formula and model, right, like we can interpret it using this interpretation function, and that gives us a value 0 or 1. Okay, so now I'm going to define this thing that's called models of F, and basically it's a set of W's. It's a set of models where interpretation function is equal to 1. So going back here, right, like looking at this, there could be one W, and I can check interpretation function of F and W. I can also be looking at a set of models, right? And I can call this models of F. And what is models of F, right? Models of F is a setting where interpretation is, it's a set of W's. So let me write that here, models of F, what is that equal to? It's a set of W's such that interpretation function of F and W is going to be equal to 1. So let me write that in the set of my definition. So we talked about interpretation function, we talked about a single model, and I don't know why this does this. Let me erase this. We have models M of F. Okay, and what is that? That is a set of W's such that interpretation function of F and W is just equal to 1. Okay, all right, so now we have our models. Let's go back here. Okay. All right, so basically, intuitively, you can think of this models of F as all the worlds, all the assignments where F holds, and anything outside of this is still like has some world, has some possibility, but that's a setting where this particular F doesn't necessarily hold. Okay, so let's look at an example. Let's say our formula F is rain or wet. Okay, so then if I think about models, all possible models are when we think about rain taking values 0 or 1 and wet taking values 0 or 1. So I can kind of like show that by this 2x2 grid. That's all possible models. But what is models of F? Models of F is when rain or wet holds, and that is the shaded area, right? So the shaded area here is showing kind of like the meaning of this formula F, which is, again, symbolically written, doesn't have a meaning, but models of F is assigning a meaning to it. So it's saying, hey, these grids is showing like what is the meaning of rain or wet. And the key idea here in logic in general is there's this formula, although it is written like again syntactically and it is a symbolic representation, it's a very compact like representation of a giant set of models, right? So in general, the nice thing about logic is we could use formulas to compactly represent like very like large meanings. Like a lot of times like exponential meanings could be represented by formulas that are pretty compact and nice. And then that is kind of the power of logic. You can write this compactly and you can do operations on it, you can do inference on it and so on. And that is really nice. Okay. All right, so that was formulas and models and interpretation functions, finding formulas and models. And what now we want to do is we want to think about how could we do operations here and how could we, what would meanings, like what would new formulas add in terms of meanings to the knowledge that we already have? So for that, let's define something that's called a knowledge base. So a knowledge base is a set of formulas that I already know. Okay, so if I have like a system, a virtual assistant system that I want to add logic to it, or I want to speak to it using language or using logic, that system has a knowledge base, which is a set of formulas that are already represented. It's a conjunction or intersection of a bunch of things that it already knows. Okay, so let me go back here and write out knowledge base as a thing. So knowledge base KB. I'm going to use KB for this. And this is a set of formulas that we already know. Okay, so we might already know a formula that says rain or snow, or we might already know there's traffic. Okay, so this is our knowledge base. So then what happens is that someone might come and give me a new formula, and what we're interested in looking at is how does that affect our knowledge base? So before getting in there, so knowledge base is a set of formulas, so it is in the syntax land. What would be the analog of it in the semantics land? It would be models of KB. And what is the models of KB? Models of KB is going to be an intersection of models of F. So maybe let's go back here. Let me just look at an example. So we looked at an example where, let's say I have a formula F1, and F1 says it's raining and snowing. Okay, and maybe I have F2, and F2 says there is traffic. Okay, let me separate these. Okay, and I have a knowledge base, and my knowledge base has F1 and F2 in it. Okay, so someone already told me there's raining and snowing, and then there's traffic. So what would be models of KB? So models of KB is going to be an intersection of models of F1 with models of F2. And why is that? Because if you think about it, right, like F1 is a formula. F1 has a set of models corresponding to it, models of F1 corresponding to it. And F2 is another formula that I'm just adding to my knowledge base. And that has a bunch of other models corresponding to it. And my knowledge base, right, like is now going to be an intersection of these two. Because as we add more formulas, right, as we add more knowledge to our knowledge base, then our models is going to become smaller and smaller because we are adding more constraints, which is pretty interesting, right? So in general, if I have, let me maybe write that in a different color. So if I have a knowledge base and I add a new formula to that knowledge base, maybe I union it with a new formula that is added, new F, what would be the effect of that on models of KB? The effect of that on models of KB is going to be what I had for models of KB, intersection models of F. So adding new formulas is constraining our models, right? Constraining the meaning more and more. Because it can't be, like, if we have raining and snowing and we have traffic as a whole other set of models, the intersection of the two is going to give me this models. Okay. So also let me connect this. So this corresponds to these models, this corresponds to these models. All right. So let's go back here. So that's how we define models of knowledge base. Let's look at another example here. So let's say we're looking at raining as one formula. Models of rain is going to be this shaded area where rain is equal to 1. And then we have another formula, rain implies wet. And what is models of rain implies wet? It is basically negation of rain or wet. So basically it is this shaded area. If I'm looking at a knowledge base that has both of these in it, then what would be the models of that knowledge base is just going to be the intersection of these two shaded area, which is basically this square, okay, where we have both rain and rain implies wet holding. Okay. All right, sounds good. And this is what I've already basically mentioned. We have knowledge base. If we add a formula to it, we increase the size of our knowledge base, we are shrinking the size of set of models because we are constraining things more and more. So we are constraining the meaning part. All right, so now let's talk about this idea of what happens if I have a knowledge base and I add a new formula. So I have a knowledge base, I'm trying to add a new formula, see what happens. And there are 3 things that can happen. So one option is entailment. So what entailment says is if I have a knowledge base, if I have KB as my knowledge base, and you come and tell me a new formula F, and that formula is not adding anything to my knowledge base, then we say we have entailment. Okay, so this is a scenario where F is just not adding any information or any new constraints. Like this is basically telling me things I already knew. Okay, so we say KB entails F, and what that is written using this double line kind of symbol. So we say KB entails F if and only if models of KB is an intersection of models of F. Let's look at an example here. So let's go back to here. Maybe I'll start anew. So we have 3 options. One is called entailment. Yeah. So let's start with a knowledge base. And my knowledge base maybe is rain and snow. So I have a formula in my knowledge base that says rain and snow. And that has models corresponding to it. So this is models of KB. Okay. And you might come and tell me a new formula, and that new formula is rain. And if you tell me rain, and I already have rain and snow in my knowledge base, that doesn't add any knowledge to me, right? Like I already knew it was raining. So then this models is going to be models of F is going to be a superset of models of KB. Okay, so we say KB entails F if and only if models of KB is an intersection of models of F. So didn't tell me anything new, already knew that, and that is entailment. So let me go back here and maybe add these under our definition. So now we have defined entailment under this. Okay. All right. So let's go back here. So rain and snow is entailing snow. So, okay, so that was one option. Another option is contradiction. So what is contradiction? Contradiction is a scenario where you're telling me a new formula F. I already have a knowledge base, KB. You tell me a new formula F, and that is contradicting with my knowledge base. Okay. So in the models land, what happens is that models of KB doesn't have any intersections with models of F. Okay. So F contradicts what we know, our knowledge base, if and only if models of KB intersection models of F is going to be the empty set, right? So let's look at an example. Let's maybe go back here. So our second option is contradiction. So let's write that here, contradiction. Cool. So contradiction is a scenario where I know some knowledge base. So my knowledge base is maybe rain and snow again. So I think it's raining and snowing. And then you come and tell me a new formula, and that new formula is negation of snow, maybe. Okay? And that contradicts with my knowledge base, right? So if that contradicts with my knowledge base, what happens is that there is a models of KB, and there is a models of F, and they don't have any intersection. So contradiction is a scenario where models of KB intersection models of F is empty. Okay. One other interesting thing to kind of like notice here is that if you think about contradiction, contradiction is very related to entailment. Contradiction is the same thing as entailing negation of F. And why is that the case? Because if you look at models of F, right? Models of negation of F is anything outside of it, right? So if this is models of negation of F, then what is happening? The thing that's happening is that models of KB is a subset of models of negation of F. And if you remember our definition of entailment, that is the same thing as KB entailing negation of F. Okay, so that's pretty interesting because contradiction is the same thing as entailing negation of F. Okay? All right, so those were the two cases so far, right? You either tell me a new formula and I already knew it, so that is entailment, or you tell me a new formula and that contradicts the knowledge base that I've had, so that is contradiction. Okay, and let's add that here. So we talked about entailment. Now we've talked about contradiction. And we wrote entailment as KB entailing a formula, and contradiction is KB entailing negation of a formula. Okay. All right. So there is a third case. Let's talk about that third case. Let me skip that. So we talked about contradiction being very related to entailment, and KB contradicting with F is the same thing as KB entailing negation of F. Okay. All right. So the third case here is what we're calling contingency. And that is when you're telling me a formula, and that formula is actually telling me something I didn't know. It's telling me some non-trivial information. Okay, so that is when models of KB has some intersection with some non-trivial intersection with models of F. Okay, so that is when we write models of KB intersection models of F is going to be a subset of models of KB, but it's going to be a strict subset of models of KB. If this is equal, like we get entailment, so we don't include equality here. Okay? All right, let's look at an example. Maybe let's go back here. So our third case is contingency. And that is when I have maybe my knowledge base, and maybe my knowledge base is just rain this time. And you come and tell me a new formula, and that new formula is snow. Okay, so my knowledge base thought it is raining, so I have my models of knowledge base corresponding to raining here. And then you come and tell me, hey, by the way, it is also snowing, and models of snowing is here, and there is some non-trivial intersection going on here. Okay, so contingency is when models of KB intersection models of F is going to be a subset, and it's not going to be equal to models of KB. And similarly, empty set is going to be a subset of this, but it's not going to be equal. So you get like some non-trivial information, something that you didn't know, and that gets added in. Okay, so that is contingency. And going back here, let me add contingency as the third option. Contingency. And contingency is when you have these non-trivial intersections. I'm not going to write it out. All right, let's go back here. Okay, so we have these three possibilities. You give me a new formula, I'm either entailing it or contradicting it, or I have contingency. So now let's talk about how we would use these ideas if we want to implement a virtual assistant. Remember, like we started this lecture thinking about having a virtual assistant where we can talk to it in logic or language. And that virtual assistant, right, like we can tell it some information or we can ask it questions. And then maybe we want to implement this tell operation. So if I want to implement a tell operation in this virtual assistant, this virtual assistant is going to have some knowledge base at the moment, some KB. And I tell it F, a new formula F. So what can happen? So if I tell it a new formula, maybe I tell it is raining. So I do tell rain. Three things can happen, right? It can either entail F, right? My knowledge base might already like have raining in it. In that case, the response to tell operation, tell it is raining, it's going to be, I already knew that. Okay, so if it says if my virtual assistant already entails rain, it should respond to me as I already knew that. Okay, if it contradicts F, it should say I don't believe that, because its knowledge base basically says it's not raining, and now you're telling it is raining, and because of that, it would respond as I don't believe that, because my knowledge base tells me the opposite. Or if you're telling it something new, you're telling it is raining and it didn't know that or it didn't have any information about it, then it should say, I learned something new. And based on that thing that you're telling it, it should update knowledge base. It should update its KB by this new formula that it is raining. Okay, so now we can implement a tell operation based on these three ideas of entailment, contingency, and contradiction. In a very similar fashion, we can also implement an ask operation. If you ask it, is it raining? Then based on that, it can go ahead and it can answer yes, a definite yes, if KB already entails F, so if we have entailment. It should answer no if we have a contradiction, if KB contradicts F, right? Or if KB entails negation of F, so it should give us a definite no that there's a contradiction. Or it should tell us, I don't know. If there is contingency, it doesn't know. So if you ask it, is it raining? It doesn't know, so it should just say, I don't know. So going back to the things we were defining here, let me move this inference rule thing. Okay. So let me just write tell and so we talked about this tell and ask operation, and we can basically implement tell and ask based on this entailment, contradiction, and contingency. All right, so I want to just do a quick side note here. I don't want to go into this in too much detail, but there is a connection between the things we are talking about here and some of the topics we discussed like 2 weeks ago in Bayesian networks, right? So we've been talking about this idea of models and having these types of models, and this is the same thing as assignments, right? And you can basically think of having Bayesian networks as a distribution over these assignments, over these models, right? I can have like A equal to 0, B equal to 0, C equal to 0, and I can have a probability assigned to that. Like probability of that could be 0.3. And I can have another assignment or model, and I can have another probability assigned to it. So from a Bayesian network perspective, from probabilistic perspective, one can think about logic in a probabilistic way and think about probability of a formula given a knowledge base. So when you have a knowledge base, you have some knowledge, and we are asking about a formula, one can think of, instead of thinking about just these three different things like entailment, contradiction, and contingency, one can think of a probability, like an actual like value, right? And probability of a formula given a knowledge base, so what is that going to be equal to? That is going to be equal to probability of models, W's, that exist in the intersection of models of KB and models of F. right, over probability of all possible models in knowledge base. So W's are all possible models in my knowledge base. I'm going to sum over all those probabilities of all possible models in my knowledge base in the denominator. And in the numerator, I'm going to just focus on models that are in the intersection of models of KB and models of F. And the union, so models of KB union F is equal to models of KB intersection models of F. That's why there's a union here. You remember, like, if you add an F to your KB, you're shrinking your knowledge base. So that's why this numerator is smaller, right? You're shrinking your knowledge base by adding this F to it. Okay. And if you think about this fraction, right, this is a number. This is a number between 0 and 1. And now we have probabilities. We have actually like a probability for F like being satisfied or not given a knowledge base. But in general, like, this was just like a quick digression, like talking about a probabilistic view of this. There's quite a bit of work actually in logic and probabilistic versions of it, and thinking about probabilistic model checking, and instead of giving just like 0, 1 values, what would be a probabilistic view of it. We're not going to go into details of those in this class. And basically, you can think of these probabilities as these 3 different ways of looking at the problem that we have been talking about. If this probability is equal to 0, then we basically have an answer of no, we have contradiction, right? Like F is not satisfied. Well, if this probability is equal to 1, if the numerator and denominator are equal to each other, then you're answering yes, right? Like F is not adding any information, so we have entailment. And if you get any other value in between, any other value between 0 and 1, then you're in an entailment situation. We are in a contingency situation, and we basically say we don't know, right? Like any of them, we basically say we don't know. All right, so that was just a quick kind of like connection to a probabilistic generalization of some of the things we were talking about and Bayesian networks. But now let's just go back to the same problem we are talking about, right? So we've talked about these 3 different things: entailment, contingency, and contradiction. We've talked about how we can have a tell and ask operator based on that. Now we're going to talk about this idea of satisfiability. So what is satisfiability? So a knowledge-based KB is satisfiable if models of KB is non-empty. Okay, very simple. Like models of KB is non-empty, we have satisfiability. Okay, so why is satisfiability useful? Why am I talking about this as satisfiability? Because satisfiability is a well-known problem. We have really good like solvers for it, SAT solvers, and we're going to talk about that in one slide really quickly. So it's nice to think about these 3 different things: entailment, and contingency, and contradiction, in kind of a view of a problem of satisfiability. Okay, so we have these 3 things. Satisfiability gives me a yes or no answer. So how can I use satisfiability to answer if we are in any of these situations? So the way we use satisfiability is we do 2 calls to satisfiability. So the first call is, in general, if I want to think about my ask operator or tell operator, and if I want to reduce it to satisfiability, I can do 2 calls to satisfiability. I can first ask if KB union negation of F is satisfiable or not. Okay, so what does the answer to that give me? So if I get no for that, right? If KB union negation of F is not satisfiable, I have entailment, right? So I get my answer for entailment here. And if I get yes for that, that doesn't answer everything, right? Like if I just get yes for this, I don't know if I'm in a contingency situation or a contradiction situation. So what do I need to do? I need to do another call to satisfiability. And the second call to satisfiability is asking if KB union F is satisfiable. And what does that check? Well, if I get no for that, then I'm getting contradiction. Remember, contradiction is the same thing as entailing negation of F. That is why the answer for this gives me contradiction. And if I get yes for that, I get contingency. So what I've just done is if I want to know if I'm in the entailment, contradiction, or contingency situation, then I can basically figure that out with 2 calls to satisfiability. And why do I want to know if I'm in any of these situations? Because that helps me implement my ask and tell operations. Okay? So going back here, so we talked about ask and tell. We talked about how it relates to entailment, contradiction, and contingency. And now we have talked about satisfiability as a way of answering which scenario we are in. Okay, and how do we answer satisfiability? So that's a good question to ask. So what is satisfiability? So satisfiability, in checking satisfiability, the SAT problem in propositional logic, is basically just a special case of solving a constraint satisfaction problem, a CSP. And we have already learned about CSPs and solving CSPs. So what that means is we can basically check satisfiability. We can basically check if the CSP problem, like what's the solution to the CSP problem, and solve satisfiability with algorithms that we already have access to. Okay, and this idea of checking satisfiability is called model checking. You're checking if a model exists or not. You're checking if an assignment exists or not. Okay, so the mapping of the SAT problem to CSPs is as follows. So propositional symbols are basically variables, what we used to call variables. Formulas are basically constraints. And then if you have variables and constraints, you can come up with an assignment, and that assignment is basically a model. So you're checking if a model exists or not. You're checking if a satisfying assignment exists or not. Okay? Let's look at an example. So let's say our knowledge base has these two formulas in it. We have A or B, and we have B bidirectional implication negation of C. Okay. All right. So we have three symbols, A, B, and C. These symbols are the same things as CSP variables. So we can have three nodes, these three variables. And then we have basically two formulas. These formulas create constraints in our CSP. So we have A or B, and then we have B equivalent negation of C. And then what are we doing? So we have a CSP, we can solve it, right? We can find an assignment, a consistent assignment for it, which is the same thing as a satisfying model. And if you find an assignment, this problem is satisfiable, model checking comes up with a model for it. And then if it is not satisfiable, it's going to return as unsat. It doesn't come up with any assignments. So that's kind of nice. Going back here, right? Like this problem that we've been talking about, this tell and ask operation, reduces to entailment, contradiction, and contingency. I can use satisfiability, two calls to satisfiability to answer that. Then how do I do that? Well, I use model checkers to do that. So that's called model checking the satisfiability, which is basically solving a CSP. Okay. All right. So going back here. Okay. So what does model checking do? Model checking takes as an input a knowledge base. And what does it output? It outputs if there exists a satisfying model or not. And if it does, it returns that model. Okay, so it checks if models of KB is non-empty. And there are a good number of algorithms out there that try to do model checking. And some of the older ones is DPLL is kind of like a well-known algorithm that tries to do satisfiability and model checking. What it does is it uses backtracking search, and quite a bit of pruning and quite a bit of heuristic goes into it to make sure that it can solve this problem as fast as possible. Some more recent algorithms are things like WalkSat that is pretty similar to Gibbs sampling, and it does a randomized local search. There are a good number of solvers out there, satisfiability solvers out there. Z3 is a famous SAT solver that you can look into if you're interested in solving SAT problems. And with that, we now have a good idea of syntax. We have a good idea of semantics. And next, what we would like to talk about is we would like to talk about what the formulas get us, right? Like, why do we live in the formula land? Like, why do we want to even look at syntax? And it turns out that we can do inference on formulas, and that buys us quite a bit. So in the next module, we're going to be talking about what formulas buy us and how to do inference rules.